I've got a bunch of different capabilities I'm going to talk about here. So this brief's about 1 mile wide and 1 inch deep. So I want to let you know that if there's something that piques your interest in here, and I'm not going to claim that I'm an expert in all the different areas that we have at Sandia, but please come see me and I will make sure that whatever it is you're interested in, I can link you up with the right person who is an expert in that particular area. So we have a whole lot of things going on at Sandia, so I'm just going to focus on what we're doing in the area of energy efficiency and renewable energy, because that's most appropriate to this crowd. You probably don't care about nuclear weapons. But just so you all know, those of you who are not familiar with Sandia, we got our start back in the 40s building nuclear weapons. Back in the days when we were first doing it, there were a couple of labs responsible for the math and physics. There were other labs responsible for building the pit of the nuclear device, the nuclear material itself. Sandia was responsible for everything else. All the material that goes around a bomb to get it to where it's going, a ballistic missile, a rocket, all those different engineering challenges that go from getting a nuclear device from somewhere here in the continental U.S. or out in the middle of the ocean, a couple hundred feet below the sea, into enemy territory. There's some significant technological challenges to doing that. And the point here is that we've taken the engineering and science that it took to develop those nuclear weapons capabilities and turned it into other things, because there's very little work in the nuclear energy business, or nuclear weapons business anymore. Nuclear energy also, for that matter. What they did in the 70s, when we started having an energy crisis, we started converting some of those engineering activities over to renewable activities. Back in the 70s, we built the first vertical axis wind turbine, and those of you who may have been in California in the 70s and 80s, you probably saw a lot of those out there in the middle of the desert. It has lost some popularity since then, but we're rebuilding that type of a device for offshore uses now. I'll talk about that a little bit later. The other things, obviously, that sprung up, the photovoltaics, the concentrating solar tower we have down there, and I'll talk about each of these a little bit. And there's a whole lot of other capabilities at Sandia that are supporting renewable energy development, because when you develop a new material that might be used for a nuclear weapon, it also might be very useful for developing a blade or a rotor that goes under the water or whatever to produce energy. So the point I was just making here is we've taken that strong research foundation that we have at Sandia and developed over the past 60 years, 70 years almost now, and turned that into other uses. We have some tremendous computing capabilities at Sandia. If you ever look at the top 10 computers that are around the country on a year-to-year basis, you'll see these published. There's usually 2 to 3 of them at Sandia National Labs. There are obviously some capabilities with effects, radiation effects, high energy. When you take something like a nuclear device, pass it through space, and then re-enter the atmosphere, you've got to go through a whole lot of different environments. So we replicate those environments, and so we have the capability to test almost anything. We can drop things, we can heat things up, we can freeze things, we can put them in high G environments, pretty much anything you want to do. And so those capabilities are useful when it comes to testing new renewable energy tools that we might want to develop. Material science, another area that I mentioned briefly, but there are all kinds of materials that we've been working on for many years that have a lot of applications. Now, in all honesty, some of those materials are very expensive, and you're not going to put a 100-meter wind blade out of a very expensive material. But there are other things you can do. The other areas of microscience, or microsystems, I'm going to talk briefly about that, bioscience, etc. So as I mentioned, we've leveraged the capabilities of the Nuclear Weapons Lab to work on energy efficiency and renewable energy activities. The high-performance computing capability is very useful when you're trying to develop a design for a new wind turbine, for example. And you put that design into a model, and then you simulate the environment that rotor is going to be exposed to, the winds and the change of the winds, etc. you can simulate 50 years of rotations and environments and changes in wind stuff in a matter of hours or days on one of these supercomputers, so you can determine whether your design is going to be worthwhile or not. And then you can actually go out and build it and test it and make sure it actually. By doing that, we can save lots of money. By modeling and simulating all the different things we build, you can save a lot of money and not have to build things that don't actually work very well. Microelectronics, one of the systems that's real exciting out there is what they call microsystems enabled PV. You can see these little specks here. Those are about the size of a drop of water, and each one of them is an individual photovoltaic cell. Now that doesn't sound like it produce a whole lot of energy, but if you put these in some kind of a clear paint, for example, and paint it all over a vehicle or a tower or something like that, you can collect a tremendous amount of energy over the surface area, things that you typically would not have been collecting energy over. It's still a long way to go with this technology, but we've already proven that it does work at a very small scale here. And now we're working on turning that into applications. I'm not going to hit on all the topics here. Number one, because I'm not an expert and I can't talk very much about it, but I want to get through all the other topics that we're going to talk about also. So getting right into some of the renewable energy activities at Sandia, the first we're going to talk about is photovoltaics. We've had photovoltaic systems since the 70s out there. Originally what we did was we took new photovoltaic systems off the shelf, put them out in the field, and we tested them. We've seen how long they would last, how quickly the surface on these things would fade, which degrades your photovoltaic capability, how you would integrate them with the grid, how you handle the storage. Obviously, when the sun goes down, they're not very useful. So we want to work on that problem. We want to develop some kind of storage mechanism so we can constantly provide energy to the grid. There are a couple of different labs at Sandia that are focused on just photovoltaic research. And then another thing that these guys are working on is integrating photovoltaics into the smart grid. We heard some talk about that in the past few days. The guys here are developing enhancements for the smart grid which are applicable to the wind energy or the water energy or the concentrating solar, any of the other renewable energies that we're working on. I'm not going to discuss all the collaborations on here other than to point out that we collaborate with a lot of companies out there. Brian mentioned his company. He's a small business here in Wyoming. He also mentioned Royal and Lori's company, Peak Spatial, who are doing the demonstration out here for us. We partner with really large companies like GE and General Motors, et cetera, but we also partner with a lot of really small companies and try to develop a small business. There's incentives for doing that, and we'll talk about that at the end here also. The impact that the photovoltaic team has been having on is primarily in the areas of developing new types of photovoltaic systems and storage and integration of photovoltaics in the grid. All areas where we have some problems in getting the PV down to the cost that we were talking about for natural gas. Obviously, everybody wants to beat natural gas. And so, I think it was Michael mentioned earlier that we've done that almost in the wind energy business. Now we've got to get all these other renewable technologies to that level also. Concentrating solar, for those that are not familiar with it, this is where you take a whole series of mirrors and you focus the energy of the sun on a point. In the case here we're talking about here, we have this huge tower out there in Albuquerque. And this was originally started not so much for renewable energy research, but to test things like the tiles on the space shuttle, to put nuclear weapons through very, very harsh environments, very, very hot environments. For example, when the space shuttle comes back in the atmosphere, it gets very hot, and those tiles are exposed to extreme heats. How do you replicate that here on Earth? Well, what we would do is we put a shuttle tile on this tower and then zap it with lots and lots of solar energy, which it'll literally melt through an inch of steel in a matter of 20 seconds or so. But so you can get some really good heat. But now, from energy perspective, what you do is you take that same principle and you concentrate the energy on molten salt or some type of liquid so that you can create heat and create steam and create energy. So this is one of the few places in the world, it's the only one in the Western Hemisphere, where you could take your new concentrating solar device and test it. There are other concentrating solar facilities here in the United States, particularly in California, Nevada area, but they are not available for testing activities. They're actually trying to produce energy and make money. So the guys at Concentrating Solar Plant have done a variety of different things. They're the best in the world, as it says here. They hold the record for converting concentrating solar into energy. Still, not as efficient, not as cheap as wind or photovoltaics, but they're making progress in that area. And potentially, this has some real potential for the future. I'm kind of ashamed of myself. I put an old picture of my wind farm up there. These towers actually have blades on them now. We commissioned this facility just about 6 weeks ago, something like that. It's our new test facility out in Lubbock, Texas. The Sandia wind program is almost entirely focused on the rotors and the blades. Our goal is to make them as efficient, as reliable, as effective as we possibly can, so that we can reduce the cost of energy. We don't worry about the gearbox and the generator and all that other stuff. There are people at the NREL, National Renewable Energy Lab, that concentrate on those things. So we work on the blade. And one of the more recent things we've been doing is developing this new test facility out in Lubbock, Texas, where we're studying turbine-to-turbine interaction. The effect one turbine has on the next turbine downwind from it. Because obviously you steal some of the energy from the wind, so the next turbine doesn't get as much. So we're trying to figure out what is optimum. How far apart do you want to put these things to make them optimum for the whole farm? We don't care about the individual turbine so much anymore. It's the whole farm. How effective can we make the farm? And it may be that you don't want to put it in right behind the turbine in front of it. You might want to put it off to the side, because there's a wake effect as the wind goes around the first row of turbines, and it actually increases the wind on the sides of that turbine and over at the top of the turbine. So it may be that we want to have a taller turbine in the second row, or a different type of turbine in the third row to accept the wind that you're getting after it's been processed by the first row of turbines. So there's a lot of work to be done there. This is the first of its kind facility. Nobody has really done a whole lot of research in this area. We believe that there's the opportunities from 10 to 40% improvement in the total productivity of a wind farm if you place these turbines appropriately and put the right types of blades on them. So there's a lot of room for improvement there. That would, when in a business that's operating on the margins, 10 to 40% improvement would be a really, really good thing. I mentioned the Swift farm. The other point that I make frequently here is that these turbines are not full-scale, the monsters you see out on the side of the road here in Wyoming. They're about 100-foot tall towers. Blades are only like 13 meters long. The point in doing that is we can replicate everything you would do on a full-scale turbine, but it's about 1/10 to 1/20th the cost of any of the testing you might want to do on a full-scale turbine. That's a really, really significant cost improvement, and it allows you to do a whole lot more tests per year than you might want to do on a full-scale turbine. A variety of other activities that we're working on there, and if anybody wants to talk about them in detail, I'd be more than happy to during the break. The thing that Brian mentioned here, one of the things we're working on right now is a problem that we have with wind turbines is that they create clutter for radars. So if you have military radars or FAA radars, etc., and you don't want clutter on those, because what happens is a plane flies through a wind farm, it more or less disappears from the screen. That's a bad thing. We don't want airplanes bumping into each other. We don't want bad guys flying into our airspace without us knowing about it. So what we've been trying to do with Brian and the DoD and FAA and a variety of other companies is try to figure out tools that will mitigate this problem. There are a number of smaller radars you could put into a wind farm and help mitigate the problem. Another thing somebody was asking about yesterday, why don't we just make the blades stealthy? Put some kind of radar absorptive material on them so that they don't reflect the radar, and so it wouldn't create the problem. And that is something we're working on at Sandia. It's a little bit challenging because you want to build something that can withstand the environment of a wind turbine operating for 20 years in the heat and the wind from dust, etc. And that typical radar absorptive materials don't work that way. And it also has to be something that's not classified. We don't want a bunch of classified blades out there. So we're taking materials that are off the shelf and putting them in new combinations so that we can absorb radar material. We've tested this on 20-inch panels, and we have identified a number of combinations of materials that will absorb the radar and mitigate the problem. We have not built a full-scale blade yet or tested, but it's one of the things we're hoping to do in the future. My sister organization is the Water Power Department, and it's very similar to the wind business because in essence you're taking a hydraulic fluid and pouring it over a turbine. It could be an underwater turbine, it could be up in the air type turbine. They're obviously different design because the materials are different that you're operating in. But they are working on ways to put smaller marine hydrokinetic devices in river channels or in channels along the straits between like New York, between Long Island and the Hudson River area. Those are already in place actually. And they're also working on things like wave energy converters, things that sit there and bob up and down in the ocean as the waves pass. And as they're bobbing up and down, we're obviously collecting the energy and turning that into useful power. So there are a variety of things they've been doing at Sandia, mostly in the modeling and simulation area. We also have some test facilities where we can simulate the erosional environments that you'll have at the base of these different types of devices in the ocean or in a stream environment. Trying to make them as efficient, as effective as possible. Again, this is an area that we're not really cost competitive yet, but there is interest and there is a potential for some areas of the country where you have a really good water resource, and I don't mean a resource like a dam. I mean channels or ocean waves, etc. Okay, I'm going to move a little faster here. The geothermal program. This is an area, somebody mentioned Salton Sea is a hot geothermal area. Our focus is not on finding the best geothermal areas. That's other people that do that. Our focus is trying to develop technology that will help you exploit that. And one of the key things that we've done at Sandia is develop these new drill bits. As you can imagine, a drill bit that has to go into a geothermal environment has to be able to tolerate extreme heats, extreme pressures, very caustic possible chemicals down there. So we've been working for several years on these polycrystalline diamond devices that can withstand that type of environment. And also the electronics. Ideally, you want some electronic systems down in there that can tolerate that environment also, so you can keep up with what's going on with your drill bit. Some of you may recall a year and a half ago or so, there were some guys trapped in a mine in China, and they drilled into that pocket where those guys were trapped and hit the pocket itself. I mean, we're talking about a 20 by 10 room and several 1,000 feet underground. You know, how do you hit a target that size without ever seeing it? What you do is you put the right kinds of sensors on your drill bit itself, and you can turn that thing and drive it to where you want it to go. So Sandia was involved in developing technology to help them do that. Obviously, for drilling business, oil and gas, there's some applications there as well. There are a variety of things we do out in our California office. We have the main office is of Sandia is at Albuquerque, California. Livermore also has about 1,000 people out there. They work a lot with vehicles activities. And when I say vehicles, it's not like we're developing a new kind of car or a new truck or anything like that. We're trying to make fuels, particularly biofuels, which is the next program here, that will work effectively with the different type of engines that the big companies are producing. So we've partnered with those big diesel engine producers, the big car companies, etc., to try to develop better fuels and use them more effectively. And they have a capability there to actually see how an engine works. They have clear panels where you can see the actual I say explosion, the burning of the fuel, and you can see how it's burning, and then change the way you do it to make it more efficient and effective. this gets into the biomass program. It's conducted at the same research facility there. And again, our concentration has been on biomass, converting it to fuels for vehicles. There's a lot of discussion, about using concentrated natural gas, compressed natural gas, etc. for vehicles. That's not our area of interest. We're trying to take biofuels and make them into use for vehicles. Another area that has been looked at sometime in the past is hydrogen vehicles and hydrogen fuel cells. We did a lot of research in that area, still do. The big concern here is you take something that's as combustible as hydrogen and you put it in every car out there. What happens if you have a car accident? Are you going to have an explosion on the road? Is it going to burn up everybody? That's bad. So we've spent a lot of time and energy on building the standards that would go into these hydrogen vehicles and the way you would store the hydrogen in the car, etc. I've also been working on hydrogen fuel cells, to produce, as you see here, light in remote facilities, etc. A lot of work going on there with hydrogen. In my previous job, I got to work on that explosives field. One of the things we did was try to make these hydrogen fuel cells detonate intentionally. That's a fun job. But the point, though, is that we want to make them as safe as possible so that if you are putting them out there in the public, they're not going to cause accidents. Another area we're working on is energy efficiency, building technologies. You want more efficient lights. So we spend a lot of time developing LEDs that are better, command and control systems for your house that would make your energy more efficient, use your energy more efficiently. One of the things they just got an R&D 100 award for is this Sandia cooler thing. Everybody knows for HVAC, you got to suck the heat out of your house and disperse it into the atmosphere. Well, to do that, you got to have pumps and you have to have fans, etc. So the idea here is to take away the most of the moving parts and not have a fan. And I'm not even going to try to understand the physics here, but in general, they create their own wind by having a core that is hot and an exterior that is cooler, and that forces the air to move just by the difference in temperature, and you can create wind without actually having a fan. That's the principle. Okay, so just to keep us on time here, I briefly summarize some of the capabilities that we have here at Sandia. There are a lot of other departments that I didn't mention here that work with the Office of Energy at DOE, doing grid integration type work, storage, trying to handle the storage problems, energy surety and security. Obviously, we've got a lot of experience in providing security for nuclear devices. The energy grid is something that we have to make sure is sure and secure also. And the last thing I want to mention is this partnership with a variety of other research and development activities. We do everything from very, very small on the order of tens of thousands of dollars. There's a KOA in eastern New Mexico who's trying to put in a wind turbine. So we have worked out with New Mexico Small Business and the U.S. government. So we contribute to their research activities so they can put in a wind turbine and more efficiently use their energy out there, because they got plenty of wind out there. I don't know anybody who would camp there, but what do I know? Okay, that's my story. I've got a bunch of backup slides, but we're not going to go into